All right, let's look at one more vertical spring problem, and then we'll move on to work done by a general variable force. One end of a light spring with a force constant little k is attached to the ceiling, and the other end is attached to an object of mass m. The spring initially is vertical and unstressed. You then ease the object down to a new equilibrium position at a distance little h below its initial position. So you're just going to slowly lower the weight down until it's in equilibrium. Next, you repeat this experiment, but instead of slowly lowering the object down, you just attach it to the spring and then release it, with the result that it will fall a distance capital H below the initial position before it momentarily stops and then bounces back up. So for part A, we want to show that little h equals mg divided by k, the spring constant. And then part B, we want to use the work kinetic energy theorem to show that capital H equals twice little h. All right, so for part A, since the mass m is hanging from the spring in equilibrium, that means the sum of the forces on the object is 0. So the spring force holding it up will equal the weight force down. The spring force is the spring constant times the distance the spring is stretched, which is little h. And the weight force, of course, is mass times acceleration due to gravity. So we have kh equals mg. Solve for little h, we get mg over k, which is what we were asked to prove. All right, this time, instead of slowly lowering the weight down, we attach it to the spring and just let go and let it fall. Well, it's going to fall all the way down, stretching the spring, and then bounce back up. So when it reaches the bottom, it will no longer be in equilibrium. The spring will give it an acceleration back upward. But we want to use the work energy theorem to show that the distance it falls, capital H, is equal to twice little h. So we just take the net work done by all the forces equals the change in the kinetic energy. Our initial kinetic energy is 0 since we're releasing it from rest. The final kinetic energy is also 0 because it momentarily stops at the lowest point. So that means we have the work done by the spring plus the work done by gravity equals 0. Well, the work done by the spring is 1/2 k times capital H squared, and the work done by gravity is just mg times capital H. So we have mg times capital H equals 1/2 k capital H squared. We divide out one of the h's and we could then solve for h and we get 2mg over k. Well, little h was mg over k, so we have shown that big H equals to little h. Okay, so why aren't they the same? Well, the first case, when we lowered it down slowly, we are doing work as well. So we are an extra force in this situation, slowly lowering it down. In the second case, we only have the spring and gravity acting on the mass, so we're no longer involved in it. And so it falls farther. But again, when it reaches its lowest point, it is not in equilibrium. So even though it momentarily stops, there's still an acceleration upward because of the spring force. All right, now let's look at the work done by a general variable force. So the work done by a general variable force, we do the same thing. We break it up into little tiny displacements, delta x. So it's the force times delta x gives us the little bit of work, delta w sub I. So then we sum all those up and take the limit as delta x goes to 0, and we get then that the net work equals the integral of f dx. So notice we get the area under the curve. So looking here at the graph, we have the force on the vertical axis and displacement on the horizontal axis. The curve drawn there is the force versus displacement curve. And we see then that that integral, of course, gives us the area under the curve between our initial position and our final position, x1 to x2. And what we're doing is, when we take the little delta x's, we're dividing that area into little rectangles. And the area of an individual rectangle is its width times its height. Well, its height is the force, the width is the delta x. And then we just sum up all those little rectangles. Well, if I just use delta x, notice we're going to have a little bit of error in the area under the curve, right? Because the rectangles don't exactly fit the curve. But if the smaller I make delta x, the closer we get to the real area under the curve. So that's what we mean by when we take the limit as delta x goes to 0, we're making the little delta x's smaller and smaller. The number of rectangles gets bigger and bigger, and we get closer and closer to the actual area under the curve. So that's what you learn in calculus when you first learn integration. We can extend that even into 3 dimensions. So in 3 dimensions, the general form for work is given by this expression here. The work is the integral from the initial position to the final position. The r1 vector is our initial position, and r2 vector is our final position, and it's f dot dr. So we have to do the dot product of f dot dr when we're in 3 dimensions. So dr vector is a differential displacement vector, and we can write that as a dx I hat plus a dy j hat plus a dz k hat. So it's a differential displacement in the I, j, and k direction. We can also write this in differential form, so we get dw is f dot dr. So we could use either one. Now notice that if the force is constant, we can pull it out of the integral, and then the integral just becomes the displacement. So we just get force dot displacement. So this reverts back to our original definition for work done by a constant force. And if our force only varies in x, we get f of x dx. All right, here's another variable force example. We have a box of mass 3 kilograms, sits on a frictionless surface, and is acted on by a variable force that's given by F equals 9x squared, I hat. Right? And the units then for the constant 9 is newtons over meters squared. So then when we multiply by meters squared, we get force in newtons. So that's the unit analysis there. So it's 9x squared I hat. The box moves in the x direction from x equals 0 to x equals 2 meters. So part A, we want to find the work done on the box by this variable force. So, of course, we have to integrate. The general expression for work done by variable force, of course, is the integral from initial position to final position of f dot dr. Well, f is in the x direction, and our displacement's in the x direction, so we just have to integrate f of x dx. So from our initial x to our final x. And so the integral then goes from 0 to 2, and our force is 9x squared, and then dx. The 9, of course, comes out of the integral. So the integral of x squared dx, of course, gives us x cubed over 3. So we have 9 times 1/3 x cubed. Well, a third of 9 is 3, so we get 3x cubed. But then we have to evaluate it between 0 and 2. And so the result then, we get 24 joules. So 2 cubed, of course, is 8, and 8 times 3 is 24. So that's where that comes from. Now part B, it says if the box started at rest, what is the speed of the box when it gets to 2 meters? Okay, so now we can apply the work kinetic energy theorem. The net work equals k final minus k initial. Well, the initial kinetic energy is 0 since it started from rest. So the net work is the final kinetic energy, 1/2 mv squared. So then we solve for v. We get the velocity then is 2k final over m. Well, k final, of course, is equal to the net work, which is 24 joules. So we have 2 times 24 over 3, and then the square root of that
gives us 4 meters per second.
All right, let's look at a simple pendulum. A simple pendulum consists of a heavy weight tied to a light string, and then it swings back and forth. The weight is called the bob, and let's say the weight has a mass m. And the string, of course, is very light, so we can neglect its mass. So looking at the diagram on the left, we have our bob with a weight downward, mg, and then there's a tension in the string, and it's displaced at an angle phi. All right, so since it moves along an arc, let's break the weight vector into a component in the direction of motion and one in the radial direction. So in the radial direction, we have mg cosine phi, and in the tangential direction, we have mg sine phi. The tension force never does any work, since the tension force is always perpendicular to the displacement. When we do the dot product, we get 0. Dot product of perpendicular vectors, of course, is 0. So the tension force doesn't do any work, and the mg cosine phi never does any work, since it's also perpendicular to the displacement. So the only component of the force that does work is the mg sine phi. Now to get the displacement, we look at the figure at the right. So since the bob is moving in an arc, the displacement, of course, is along the arc. So we need a little bit of arc length. Well, arc length is radius times the angle in radians. So our little bit of angle then is d phi, and then the radius, of course, is the length of the string, L. So ds is L d phi.
All right, let's look at, say, a swinging pendulum, simple pendulum. So we have a mass attached to a very light string, and it swings back and forth. All right, so here we have it displaced at an angle phi. We have a tension in the string, and then we have the weight down. So the only forces acting on the pendulum bob now are the tension in the string that points toward the point where the string is tied, or the pivot point, and then we have the weight that always points straight down. Okay, so since we're going to move tangentially to the curve, right, we break the weight vector into a component that's tangential and a radial component. So the radial component is mg cosine phi. The tangential component is mg sine phi. So the tension force does not do any work, since it is always perpendicular to the displacement. So the only force we have in the direction of the displacement is the mg sine phi. Now, our differential displacement, ds, is going to be a little bit of an arc length. So if you recall, to measure the length of an arc, we just take the radius times the angle. Well, the angle is d phi. The radius is the length of the string, little l. So L d phi gives us the displacement along the arc. So our displacement is ds, which is L d phi. Only the angle changes, the length doesn't change. All right, so the weight force is the only force that has a component in the direction of the displacement, and that, of course, is mg sine phi. So the work done is just that component of the force times the displacement. The displacement is minus L d phi. The negative sign is because the angle is decreasing as it swings down. So the work then by gravity equals the negative of the integral from the initial angle to final angle of mgl sine phi d phi. All right, now notice that this will turn out to be a positive value as the bob swings down, because our final angle is going to be smaller than the initial angle, and so the integral will give us a negative number, and then the negative of the negative number makes the work done by gravity positive as it swings down. And as it swings up, the angle will be increasing, and we'll get a negative value for the work done by gravity as it swings back up on the other side. All right, now we're going to introduce a new term, and this is called power. Power is a measure of how fast work is done. So the amount of work itself is important, but the rate that you can do the work is also important. So look at a simple example. Suppose you are a real estate developer and you want to build an office building and make money by renting out the offices. So what matters is not only how much work it takes to get the building completed, but how fast they get the building completed is also important. So the rate that the work is done is important because you can't start earning rent money until the office building is complete. So the rate that the work gets done is also important. So the equation for power is the work done divided by the time to do the work. And so looking at the units, work units of course are joules and time is in seconds, and the power unit is called a watt. So 1 watt is 1 joule of work per second. So again, 1 watt is 1 joule of work per second. And it's named after a person, so we use a capital W to represent a watt. The person, of course, was James Watt, who was famous for the steam engine. All right, now consider you have two engines. You have a 1 horsepower engine and a 2 horsepower engine. The 2 horsepower engine can do the work twice as fast, which means you can do the same amount of work as a 1 horsepower engine in half the time, or you can do twice as much work in the same time. All right, so power is the rate of doing work. So average power we can write as the total work over the total time. Instantaneous work then is dW dt. The units, of course, is a watt, where 1 watt is 1 joule per second. Now, watt, of course, is named after a person, so we use a capital W for the symbol for watt. The person, of course, was James Watt. James Watt is famous for the steam engine. He was a British scientist and engineer. Now, when I was in school, I was taught that James Watt invented the steam engine, and later on I found that that wasn't true. He did not invent the steam engine. A man by the name of Newcomen built the first steam engine. But steam engines were not very practical, not very efficient, and they could not run for long periods of time because they would get hot very quickly and would not work very efficiently. Well, Watt developed a new type of steam engine that made the steam engine much more reliable and much more efficient. And so Watt's steam engine became very practical to use. And so people started using Watt's steam engine. And so he was famous for that modification on the steam engine that made the steam engine much more practical to use. Another unit we use for power is called the horsepower. And horsepower is equivalent to 550 foot-pounds per second, or 746 watts. Well, back in Watt's day, engineers figured out how many horses they could replace and do the same amount of work in the same amount of time with the steam engine. Right? And that's where the horsepower came from. So they used to use horses or mules to do the work. Like in mines, the horses or mules could be hitched up to a mine car and pull the ore out of the mine. So they could also be used to pump water out of mines, but you could hook horses up to a big capstan, and then the horses walk around in a circle and winds up a rope that can pull stuff out of the mines and so forth. So they figured out how many horses you could replace with the steam engine and get the same amount of work done in the same amount of time. And that's where the horsepower came from. Alright, so we can write instantaneous power as dW dt. Well, the dW, of course, we could write as F cosine theta dx. So the F cosine theta gives us the component of the force in the direction of the displacement. So F cosine theta dx. So we have F cosine theta dx dt. Well, dx dt, of course, is velocity. So we could write instantaneous power then as the F dot v, where we take the force vector dotted into the velocity vector. So instantaneous power is F dot v, and average power is F average dot v. So this is another way that we can look at power. All right, let's look at an example. We have a crane hoist lifts a load of 1 metric ton to a height of 25 meters at a constant speed in 9 seconds. What is the power delivered by the crane hoist? Well, we can write the average power is the work over time. The work, of course, when we lift an object is mgh. It's the gravitational force times the distance when we lift something against gravity. So mgh over t. A metric ton is 1,000 kilograms. So 1,000 kilograms times the g times the height, 25 meters, divided by the 9 seconds, gives us 2.7 times 10 to the 4th watts, or 27 kilowatts. So that's the power delivered by the crane hoist. All right, let's look at it in terms of F dot V. Well, the velocity is 25 meters divided by the 9 seconds, since we go at a constant speed, and that's 2.8 meters per second. Okay, so the force is mg dot v, and we get the 1,000 kilograms times the g, 9.8 times the v, 2.8 meters per second, and again we get 27 kilowatts. All right, another term that's important is called the efficiency. The efficiency is the useful work output divided by the total energy input, and it's usually expressed as a percentage. So the percent efficiency equals the work output over the energy input. So we want the useful work out divided by the total energy in. And then that ratio, of course, is going to be less than 1. So to make it a percentage, you multiply by 100. So that's the efficiency. So the greater the efficiency, the more work we get out compared to the energy that we put in. So in all practical machines, the efficiency, of course, is less than 100%, because some of the energy input always gets wasted as heat. So either by friction, or if it's completely electronic, of course, currents in wires create heat. So resistance of wires creates heat as well. So some of the energy we put in always gets wasted as heat. And so we cannot have 100% efficiency. Unless, of course, you're making a heater, right? If you're making an electric heater, all of your electrical energy will be converted into heat. So that can be 100% if what you want out is heat.
All right, so again, power is a measure of how fast work is done. And the equation, of course, is power equals the work done divided by the time interval to do the work. And work causes a change in or a transfer of energy. So we can also write power as energy transferred over a time interval. So for example, we use electrical energy in our homes and businesses to convert into other forms. So for example, if you want to bake a cake, you want to make a cake, so you use an electric mixer to mix up the batter. Well, the electric mixer, you're converting electrical energy into mechanical energy, the spinning of the beaters. And so power can be the transfer of electrical energy into the mechanical energy. And power, of course, is measured in watts. All right, so that's going to be the end of this video. In the next video, we'll look at more examples of power, and we'll also look at the cost of running electrical appliances. Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel, and please subscribe. I hope you find my videos useful.